Let's jump right into this explainer. Today, we're tackling the absolute first and objectively the most crucial step in safety engineering. We're talking about hazard identification, or as we call it in the industry, HazID. This isn't about guesswork, folks. It's a highly structured methodology, a systematic breakdown to make sure the incredibly complex systems we rely on every single day actually operate safely.
You know, safety is often defined simply as freedom from unacceptable risk. But how do we actively achieve that? Like, how do engineers stare down a massive, complex network of wires, software, and heavy machinery and accurately predict what could go wrong before a single switch is even flipped?
Well, here's our roadmap to answer that. We'll start with the first safety step. Compare empirical versus deductive phases, step inside a HazID workshop, look at seeding with guidewords, and finally, wrap up with building the hazard log.
All right, let's kick things off with part 1, the first safety step.
So we define a hazard pretty simply as an accident waiting to happen. It's a potential source of harm. Now, this is a really vital distinction to make right out of the gate. A hazard is not the accident itself. For example, picture a railway crossing with absolutely no barriers. When a massive train approaches, that right there is the hazard. The accident hasn't actually happened yet, but all it takes is a trigger event, like, say, a car driving up, to unleash that harm. Our ultimate goal? Find those hazards way before the trigger ever occurs.
Moving on to part 2, empirical versus deductive phases.
In the industry, there's basically a two-pronged attack used to identify these latent threats. First up is the empirical phase. This is where we look backward. We're essentially exploiting past experience, leveraging massive databases of historical data, defect logs, and comprehensive checklists. We're asking, hey, what has failed before in systems like this? But then we have the deductive phase, and this is where we proactively look forward. It involves deep brainstorming and structured what-if studies to predict entirely new modes of failure that, frankly, historical data just can't warn us about. You absolutely need both, the empirical to learn from the past and the deductive to safeguard the future.
Which brings us to part 3, inside a HazID workshop.
During one of these deductive workshops, a team of experts systematically breaks down the entire operation. And let me tell you, it's not just a casual chat over coffee. It's a highly structured, rigorous audit. The team meticulously considers 3 major areas. First, every single system function. What is this machine actually supposed to do? Second, user operations and reactions, meaning how do humans interact with it? And crucially, how might the general public react under stress? And third, interfaces with other systems. Exactly where does this piece of equipment connect to the outside world?
To kind of ground this in reality, imagine applying this systematic review to this simplified station fire panel diagram you're looking at. The experts don't just stare at that red box in the middle. Oh no. They scrutinize its connections, the manual actuator triggered by a passenger, the fire dampers, the ticket gate lines, the lifts. Literally every single arrow you see here represents an interface that has to be analyzed. It's like a giant puzzle.
Now, I need to point out an absolutely crucial distinction here. Do not confuse the cause with the hazard itself. If a team mixes these two up, they end up with this massive, unmanageable list of pseudo-hazards. Going back to our fire panel example, a failing power supply, well, that's a cause. The actual hazard, the condition that directly leads to harm, is that no alert gets sent to the interfaces. See the difference? Focusing on no alert lets engineers design a robust safety measure, rather than getting totally bogged down by 1,000 different reasons why the power might have dropped in the first place.
All right, part 4, seeding with guidewords.
What's really fascinating here is how incredibly simple words can unlock these highly complex engineering solutions. By seeding the workshop conversation with guidewords like no, more, or reverse, the team actually forces structured what-if scenarios. Take a fire damper that's meant to close off airflow, right? Apply the guideword no, and the damper does not close. Boom, that's a hazard. Apply reverse. What happens if a vital fire damper somehow opens wider and actually feeds oxygen to a fire? This method ensures absolutely no dark corner of the system's logic is left unexamined.
And that leads us to our final step, part 5, building the hazard log.
Every foreseeable hazard identified by these experts is systematically recorded into a hazard log. But listen, this isn't just some document that gets filed away in a drawer and forgotten about. No way. It is an essential, living directory. It tracks the details of the hazard, the potential causes, and most importantly, the exact controls and safety measures put in place to manage it. Think of this log as the central nervous system for safety assurance. It tracks the management of these risks throughout the entire life cycle of the project, from the early design phase right through installation, testing, and decades of daily operation.
So, as we wrap up this explainer, I want to leave you with a final, slightly provocative thought to challenge your perception of the engineering that surrounds your everyday life. The next time you walk through a crowded train station or step into an elevator, just remember the deductive rigor, the guide words, and the hazard logs working silently behind the scenes. Are those systems perfectly safe, or are the triggers just being masterfully kept at bay?